Kia ora, hi everyone. Welcome to the 2025, the 10th 2025 webinar for specification practice for mass timber, presented to us by Matt Davies, the Technical Director from Homes today. Thanks to all our sponsors at that point that kindly support the Timber Design Society to make these events and others happening. The next webinar we're looking at will start in 2026. So we're moving into a well-deserved break over Christmas and starting the next year strong with a webinar about fully threaded screws presented by Eurotech. With exciting news, the Timber Design Society would like to announce here that the Timber Design Awards will return in 2026. So save the day, 26th of June, the entries for the awards will start shortly and updates to follow. Unfortunately, we had to postpone the Auckland event to next year. So keep an eye out for the postponed date. It's looking like March 2026 at the moment. And as usual, if you have any suggestions on technical notes and topics of interest, anything that bugs you or has come across your desk and you would like some clarification on, send us a quick topic of interest that you would like to get some clarification on in the TDS journal. And now let's kick off with the actual webinar, Specification Practice for Mass Timber. Today, Matt Davies will bring us into a detailed journey through specification of mass timber, not only CLT, but also LVL and glue laminated timber. Matt Davies is a technical director at Homes. He's a chartered professional engineer with 2 decades of experience and working with mass timber and any products related to it. This experience comes from a wide range of projects covering small-scale residential alterations through multi-story buildings. So, Matt, I will hand it over to you and get you to start the webinar.
Cool. Thank you. So that should be up and running. Cool. Yeah, thanks, Bjorn, for the intro. So when I was asked about putting together this webinar, it seemed to me that the most immediate challenge was going to be how to make it engaging. Specifications are not a particularly exciting sounding topic, and one way that I've thought to try and do this is by coming up with some sort of common themes that we can use to keep in touch with the big picture, and then sort of link some of the technical detail to those things. I've developed these themes based on, I guess, many lessons, both positive and educational over the years. And while the ideas, I guess, I'm putting forward here, they might not be for every engineer, they might not be for every project. They represent an approach that I have found is the most likely to lead to positive outcomes for projects and for buildings. So let's get underway with that. So the first theme I was wanting to introduce is that rebellions are built on hope, but our buildings don't need to be. New Zealand's building code compliance framework for mass timber is still developing. It contains gaps, and to demonstrate our buildings meet the performance requirements of the Building Act, we need to fill these gaps. We don't want to hope that we are being conservative, and we want to stay away from that shall we right sort of attitude. So I've put this table together with the idea that it will help show these gaps. There's a column each for glulam, LVL, and CLT. And I've also included a column for structural steel on the right-hand side for comparison purposes. And for reference, I've also included what I call the MB pyramid over on the right. If we look at the right-hand column, which is the structural steel column, we can see that there is a complete pathway of standards that are interlinked and cross-referenced. This means that if we work from the bottom of the column upwards, if my building has been erected with the tolerances in the erection standard, if its components have been fabricated in accordance with the fabrication standard using connectors and materials that comply with the manufacturing standards, then we can assume that then we can expect the assumptions made in the design standard are reasonable, and we can expect that the as constructed structure will resist the loads prescribed in the loading standard. So this is what is considered a harmonized set of standards. It's kind of a top to bottom, bottom to top pathway, and everything kind of interlinks together. I should probably note with this table, even though there's lots of rows and columns, it still only covers B1 structure. It doesn't cover B2 durability or fire compliance requirements. So very mindful that we've only got sort of a 1 hour window to fit this webinar into. So is this idea of a compliance pathway, is this just somewhat of a bureaucratic, nerdy paperwork exercise? Unfortunately, it's not, and we do need to make sure we are working with harmonized standards, or that we do the work to bring together disconnected standards and create a harmonized compliance pathway. A simple example that I like to use to explain this is to consider a 4-meter high glulam column. We have designed our column to NZS as 1720.1, say, which assumes the glulam is manufactured to the combined AS NZS 1328 glulam manufacturing standard, and that permits the glulam to deviate by plus or minus 5 millimeters from a straight line. So our column could have a bow of 5 millimeters halfway up its height, and in terms of for our 4-meter high column, that corresponds to a bow of height over 800. So let's say we receive an imported product, a glulam column that's been manufactured to the European glulam standard, EN 1480. This standard has a different set of allowances. So it allows an initial imperfection up to height over 500 for the column. So that would be a bow of 8 millimeters at the column height. So, I mean, 8 millimeters is obviously greater than 5 millimeters. And the initial imperfection in our imported column would be could be 60% greater than assumed when we've calculated the design capacity to our New Zealand standard. So with this example here, if we look at this chart here, which is the buckling curves for a concentric, perfectly straight column to begin with, up the top, and then as we have increasing eccentricity due to the increasing out of straightness, we can kind of see how the allowable stress that column can carry decreases. So if I've got 60% greater than assumed eccentricity or out of straightness, I've potentially dropped down to here, and I've lost about 10% of my design capacity. So if we're looking at a high-performing, optimized mass timber structure, then having our columns being 10% weaker than we were expecting, that might be very important to us. So that is kind of the importance, I guess, of linking up all our standards and making sure we've got everything harmonized and we understand the differences between them. This is of course, it's just one parameter and one example. It's certainly not saying we should avoid using novel or imported products. It is intended to highlight how we need to be cautious when we're picking a design standard from one jurisdiction, then using a manufacturing standard from a different jurisdiction. Okay, so we've established that, I guess, that with that example that the harmony between our standards is important. And if we look at what the steel industry has got, then we can see they've kind of stolen a march with their standards being harmonized and well sorted. So what gaps do we have in the mass timber compliance pathways? How do we plug these gaps? Like I said before, the answer shouldn't be that she'll be right. We're working with that theme that we don't want our buildings to be built on hope. For LVL, there's the Australian Design Standard that we can bring in, or we can use NZS AS 1720. The loading standard and the LVL manufacturing standards are both AS NZS joint standards. So we have a harmonized approach in the top half of the table, at least for LVL. For CLT, there are a couple of overseas standards that could be utilized for design, and they each have an accompanying manufacturing standard, and that's great. Again, there's some harmony between the materials manufacturing and the design. We just need to have that care about mixing and matching between, say, designing to a North American standard but manufacturing to a European standard. Connectors, so for connectors we do have some options. Mostly they're Australian standards that are referenced by the Australian Design Standard if we want to try and stay local. However, the types of these connectors are, I guess, the type that we perhaps aren't commonly using in mass timber construction. The small size screws, coach screws, nails, much more common in light timber framing. So we generally use a lot of specialist proprietary screws instead. The properties of these screws are typically declared as part of a European technical assessment or an International Code Committee evaluation report. And again, they're sort of, I guess, was harmonized to their relevant jurisdiction, whether that be North America or the EU. And so that's sort of setting us up okay. The bottom two rows, however, of this table is where it gets quite tricky. I'm not aware of any standards relating to fabrication or erection of mass timber structures. There are various guidelines around that discuss it in general terms, but they don't give the specificity needed to be used in a kind of tight contractual type of specification. So I mean, there's a lot of, I suppose, looking at the advice, doing a review of that, there's lots of that qualitative advice telling us to allow for tolerances and how important they are, but there are very few hard numbers on what a reasonable tolerance actually is for some of these elements. Myself, so I've had a few dumb moments, you could say, trying to specify erection tolerances. Some of those early mistakes are mistaking that CNC manufacturing tolerances are also the erection tolerances. The column can be positioned plus or minus 2 millimeters. And I guess the journey I've taken myself on to begin to solve the last two rows of this table has kind of involved reflecting on the purpose of the specifications we're preparing. And it's a cliche, but I guess we probably need to challenge ourselves to think about what good looks like in the context of a specification for mass timber. So my possible, like we could say, cynical take on current practice is that as designers, our specifications can end up being a master template that contains lots of references to standards, and probably half of them we don't have access to and we haven't read, we don't actually necessarily know what's in them. It's got paragraphs of boilerplate text that we've borrowed from other trades. Again, because there's a lack of published information out there, we're doing our best to cobble these things together from other parts. And the phrase "the contractor shall" is used extensively, at times perhaps to cover over areas where we're not quite sure what should be done or what needs to be done or the like. So the other thing is, I suppose, these templates that we have, they often have accreted various clauses that have come about from lessons learned. It's us sort of going, oh, we're not going to get caught by that again. We need to write something into our spec. And then we sort of get these quite heavy-handed and long templates. And we have the outcome of this is, I guess, like the image shows there, we've got this wonderfully thick specification. And the unintended consequence of this, I suppose, is that this big, thick specification becomes more of a paperweight in the corner of the site office. In some instances, it only gets opened when there's an issue, and the designer and the contractor want to kind of throw these clauses around at each other and argue their case. And then following that through, inevitably the client gets drawn in, the client gets unhappy, and we run the risk that the client will proclaim that mass timber buildings are too risky, too difficult. And of course, this isn't necessarily a timber specific issue. But the purpose of us being in this webinar is to think about how we can advance timber construction and move away from that perception that these mass timber buildings are too risky and too difficult. So with some introspection, then there's an opportunity for us to work out how we can make our timber structures specifications superior to other materials, how we can take ourselves away and off the pathway of trying to create a 60-page specification. So that leads me into my sort of second theme for the session, and that is to view our specification as a communication tool. And what do I mean by that? So what I mean is that we can approach the specification as a document that communicates assumptions, limitations, and expectations. We know that mass timber is an emerging technology, so I think we need to be as transparent as we can with what we know, what we have assumed, and what we don't know. And we need to treat it as a journey that the project team is all on together. That is a slight shift in thinking. It's sort of, to some extent, putting yourself out there and on the line and acknowledging that we don't know absolutely everything ourselves, and that we need input from others and review from others to develop these things. So I've put an example there to try and illustrate how we might adjust some of our approach or wording to be something that's a little bit more useful to a contractor. So I suppose a historic clause that I've the example is we've got a connection there. It's a large timber beam. We've created a steel cleat by slotting it into the timber. There's some bolts through the timber, through the internal steel cleat, and we've put some reinforcing screws there in red to prevent splitting and provide some robustness to the connection. And what we might, I guess, traditionally say, or have tried to say in the past, is something like the contractor shall maintain the moisture content below 15% for the duration of the works. What I suggest that perhaps we can say instead is a little bit more transparent and communicating intent more, and that is that I could say that the design details include an allowance for movement associated with moisture content change of plus or minus 4% after installation of the screws. Both of these prospective clauses, they have the same intent. They're both intended to ensure the screws are protected from excessive tension forces once the timber swells due to an increase in moisture content, but they do it in different ways. The first sort of example clause there is very prescriptive, and it's quite opaque, whereas the second prospective clause, it communicates the limitations of the design, and it creates more of a performance requirement rather than that kind of prescriptive limit. So this matters because, in short, constraints are equal to costs. The more we constrain a fabricator, the more we constrain a contractor, the more we build cost into our design. So ideally, we want to communicate our assumptions so that the contractor can use their smarts to develop an efficient process. to use this moisture content example again, the first clause could result in the contractor creating a tented temporary structure, which would come at quite high cost because they're working very hard to keep that moisture content below that limit. But instead, if we provide this second option here, we communicate assumptions and intent, a smarter contractor can pick that up, and they can instead they might defer installing those final fixings until a later stage. So the beam might be in place for 6 weeks or so on site. The moisture content will come up naturally, at which point they put those screws in place, and can monitor the variability of the moisture content beyond that point. So if we're again communicating some of our why and some of our assumptions, then that helps with that planning, and we don't inadvertently push costs onto our project. So what else do we want to be using in our communication tool? There's our specification. There are some historic pain points that I've probably singled out here. They're relating to moisture management, shop drawings, tolerances, and finishes. I've got a brief slide on each of those main ones to talk through. So moisture management or weather protection. The key things we want to talk through there, and I will reference, there's a really good webinar that Bjorn presented, which was number 1 in the 2024 webinar series. What we need to communicate when we're talking about the moisture management is, as per the earlier slide, what can the design accommodate? Is this plus or minus 4% from installation of the screws, or is it something different? What is an upper bound on moisture content that might be related to the initiation of mold growth? We may not want to see the moisture content ever get above 19 or 20%. Are there any connections that need extra care? So, for example, if we've got some very restrained, high strength, case hardened fasteners, if they are at risk of having water ponding near them, then we're creating an elevated risk of environmental hydrogen embrittlement. So do we want to communicate that risk so that it can be identified and dealt with, because that is quite a nuanced technical thing. So we want to do what we can to communicate these assumptions and limitations to a contractor nice and early. And then the last bullet point there, so instead of having a sort of catch-all contractor to develop a moisture management plan and manage all the risks for us, et cetera, I think we need to be a bit more collaborative and talk about the expectations of what we are wanting in that moisture management plan. So for those, I think there are some minimum requirements that we want to put forward, and I've sort of listed these out and put, I guess, the reasoning for those as well. So we want the contractor, as part of their moisture management plan development, to identify the target moisture contents at the different phases. So in fabrication, transport, erection, and then when the waiting time between erection and the bit of building being closed in. That's communicating the expectation that there's some that we're expecting them to plan ahead. We're asking them to outline their data collection methods, how frequently they're going to collect that data, how frequently they're going to report back to us in our construction monitoring role, and what format we want that reporting to be. So again, part of that is we're communicating that there's an assumption that there's going to be a feedback loop around that moisture monitoring data. We want them to identify possible sources of staining. So for example, rust marks or tan lines. Tan lines, I guess most commonly being if there's a prop or something of that nature. against a column, and it's columns out there standing in the sun. Then we get a kind of a reverse tan line, where you get a darkened patch that hasn't been blonded by the sun where the prop was fixed. So you're getting them to, or requesting that they identify the possible sources of that. We're communicating that expectation that the visual appearance is important. We want to request them to identify the proposed drying methods if the moisture content targets are exceeded. Again, the why and behind that is that we're communicating the expectation that corrective action will be needed if the targets are exceeded. And then finally, we want to get them to include a contingency plan within this moisture management plan. So, if as an example, if a site was closed for 12 weeks due to a COVID lockdown, or some other type of event, but what is the plan? How is that dealt with? And this again, that communicates there's that expectation of planning ahead, and what we want to see and how we want risks to be identified and managed. So it's not prescriptive, but it is still sort of, like I said, communicating those expectations, communicating our assumptions around getting feedback throughout the process. Shop drawings. So shop drawings, to be honest, based on experience, this one probably needs 2 grumpy cartoons. We often, perhaps as an industry, we're a little bit guilty of reproducing boilerplate text from our structural steel specifications, and these include like a long list of quite detailed requirements and insist on 2-dimensional shop drawings. What this can do is it will add some costs to the fabricator. So the mass timber production utilizes a lot of 3D modeling to feed into computer-controlled cutting and drilling and milling equipment. So the 2D shop drawings that we are insisting they create is often it's a bit of a side quest. The drawings will get created for the purpose of satisfying the specification. They'll get reviewed and then they'll be set aside because everything is based on a 3D model in terms of running that machinery and doing the actual fabrication. So, thinking about, well, what do we actually want to see in these from the shop drawing process? Why do we do it? The purpose isn't to have these 2D drawings. The purpose is actually for us to, find reasonable grounds to believe the fabricator has understood the design intent and then correctly applied it across all the details. If we have multiple suppliers, we have some LVL beams, some CLT floors, some glulam columns, and maybe some structural steel cleats and connections that join it all together, we can potentially end up with 4 separate sets of 2-dimensional drawings, one for each set of components, and we can end up with one connection that's actually spread across 4 different drawing sets. It's not particularly efficient to produce, and it's also not particularly efficient to review. So thinking about better ways to achieve this purpose, instead of prescribing what must be on 2D drawings and prescribing that they are 2D drawings, could we communicate what it is that we need to see to complete our review? So, again, trying to remove some of those constraints. What we are most interested in is the material grades, the sizes of the components, perhaps the screw types, the positions, any preparation requirements like pre-drilling. So for reducing those constraints and focusing on what the purposes of generating these shop drawings and shop drawing models from our perspective, it actually opens up that possibility that the shop drawing review could be completed using a federated 3D model instead of 2D drawings. So this is, in a lot of instances, it's something that is being produced anyway by the fabricators. So for them to share that with us and for us to complete our review based on that model, it creates efficiencies on both parties, and it's again avoiding our, I guess, traditional requirements, imposing additional costs onto the project. And yes, tolerances. So tolerance, it's a word that certainly gets thrown around a lot, usually a sort of pejorative undertones when it's directed towards consultants. Where the difficulties have historically come from, and I mentioned this before, is mistaking the plus or minus 1 millimeter, plus or minus 2 millimeter CNC manufacturing tolerances for erection tolerances. So this might be allowing a 2 millimeter gap between a beam and a column, which is, makes sense if you're joining those two columns, those two elements together on the floor in a lab, but doesn't make much sense when you're kind of maybe 2 stories up on a windy day in Wellington, trying to line things up while they're bobbing around on a crane. So we've got sort of 3 sets of tolerances, and that's how I think about it anyway. So we've got the manufacturing tolerances. So this will be I guess the alveol beam or the gluteum beam in the pure sense. It's a slab of timber that's cut to the sizes we need by that manufacturer. These are reasonably well covered by the material standards in terms of straightness and dimensional other dimensional tolerances. We then have fabrication and assembly tolerances. So these, so I define these as when we are bringing 2 things together to make an assembly. These aren't covered by standards. So my example that I've sketched here, put on the slide, is a steel plate that is slotted into the end of the timber beam. It has to consider the manufacturing tolerance on the plate. Both the thickness of the plate will have some tolerance, and the flatness of the plate will have some tolerance. It might have a slight warp to it. The manufacturing tolerance on the timber slot will need to be considered. There's a variability on that width, and again the straightness of that slot. And then there'll be some paint coatings typically on the steel. So and then of course with anything timber, there's the potential for some moisture movement of the timber between the manufacturing and the installation of the bracket. And we've probably all seen the instances where these cleats or plates are just too tight, and someone's either trying to drive it in with a large sledgehammer, or they just aren't fitting. We haven't left enough space. So my proposed approach for that is that, again, we communicate our assumptions. So the example there is that the connection design has allowed for the slot to be 6 millimeters wider than the nominal thickness of the plate, and that's based on the sum of manufacturing tolerances for the steel plate, the timber slot, and a nominal allowance for coatings. Again, I guess we're sort of stating our assumptions. That puts that out there. The fabricator, the contractor, can see that. They can review that. They have an opportunity to put up their hand and intervene if they need to. So yes, we're perhaps, like I said, putting ourselves out there a little bit, but we're also being very transparent and giving everyone the opportunity to identify if there's a challenge, and intervene early in the process. And then the last one there, we've got erection or global tolerances. So these are probably the trickiest. Very little guidance around. I found it can be useful to learn from Big Brother. So by this, I mean we can get some guidance from different materials that also use extensive prefabrication. So I guess an example might be the plumbness of a steel column. There's suggested tolerances for these in AS/NZS 5131, being the structural steel erection standard, and that's in my mind, I suppose, a reasonable starting point. We know that those tolerances have been used and they've been worked to for a number of years. So it seems like a reasonable expectation that someone who is rigging and installing a similar size or type of element is able to achieve that level of plumbness. And I mean, ultimately, the best source of information there is to go and engage with a contractor. But again, but realistically, we don't always have those opportunities for that early engagement. Varies client to client. So these tolerances that we put together and assumptions that we state, they won't be perfect. But as I was saying before, if we communicate what we have allowed for, then it provides the contractor with more tools to work with. It also shows that we have made a reasonable effort to ensure buildability of our design, which is often very important if it doesn't fit. But wait, there's more. So the assumptions made along our compliance pathway, they all need to be communicated to the manufacturer, the fabricator, the erector via our specification. So there's a very long list of things relating to connection design. Have we assumed that the glued beam is homogeneous? If we assume it's SG10 all the way through when designing our connections. If we have, then we need to communicate that assumption. Our screws or our connectors, particularly sort of, I guess, installation methods. Is there an expectation that a torque limiter would be used? A question that came up reasonably recently for us on a project was, how do you define a snug tight bolt going through timber? If it's tightened up following the structural steel standards, the washer will crush into the timber. So what is the definition of snug tight for a bolt in timber? What tolerances have we allowed for in our screw locations? Or have we worked to the absolute sort of bare minimum edge distances? And similarly, what have we allowed for in the tolerances for the angles of the screws? And have we designed assuming pre-drilled holes? So there's quite a lot within that we probably just sort of assume and carry on with while we're doing our different calculations, but we need to, I guess, keep track of that and make sure we are recording and communicating those assumptions and getting that information across as early as we can. There's also visual expectations and fire performance expectations and quality control and quality assurance. So communicating our expectations about roles and responsibilities, who is doing what checks. There's ourselves perhaps doing a construction monitoring role. What is our expectation of the main contractor, the fabricator, and potentially a third party accreditation service at the manufacturer, making sure that our base starting product has those factory production controls in place and giving us a reliable product to start from. So there's a lot in there, I realize, and quite a short bullet point list. And it includes a few proprietary items as well, or items that are very specific to the manufacturer. So this is probably, and that is taking us towards the third and final theme we've got this afternoon. And I guess if we want to define the problem that we're trying to solve with this theme, I've used a Venn diagram. So on the left, we've got technical compliance. So that was that heavy looking table from earlier on. On the right, we have the products that the market supplies. And obviously we need to operate in this middle zone where the two overlap. They are shown quite far apart, but that's kind of for clarity rather than a judgment view on the market. But this is one of the big challenges in the mass timber space for us in New Zealand. We often design using a diverse range of standards and guidelines and research from various jurisdictions. The products available to us are also manufactured to a similarly diverse range of standards or proprietary accreditations. Over time, as the market grows and our compliance systems also grow, then these two circles should begin to come closer together. and things will get easier. But for now, how do we approach this? I think there are two ways. There's I suppose, a traditional approach, which is that we come at this diagram from the left-hand side. This is completing a design, go to the calculations, preparing a traditional specification that relies on some of those standards we've used to do that design. That might position us with the blue crosses there. And then the sort of the follow through to that is we'll often end up having to squeeze the manufacturers or the fabricators to align what they are producing with what we have come up with. And there's plenty of precedent for this approach, and there's many award-winning buildings that have done this. However, I don't think it is going to be sustainable, and in my view, it doesn't really set the timber industry up to thrive. If we have to relearn how to build a building every time, then it will take a long time to find the efficiencies that we know are out there. Interestingly, when I was at Woodworks about 2 weeks ago, the manufacturers that were in attendance there were promoting a similar message. And so my third and final theme for the webinar is to meet the market where it is. The idea here is to start on the right-hand side of the column. We should be evaluating the products that are available to us and the compliance pathways that those manufacturers have already established. So essentially we want to select options from the right-hand side that are already grounded in this overlapping center zone and operate in that space. So again, if I come up with an example for that, if we have a cross-laminated timber CLT floor diaphragm, there is good market coverage for CLT floor panels that have got established compliance pathways for gravity loads. Some suppliers have done that by testing to manufacturing standards to determine design properties. Others have done that by testing whole panels to develop span tables, and those are supported by a deemed to comply product certification, like a code mark or something similar. And that's, there's a number of manufacturers supplying into New Zealand who could achieve that. However, there's a much smaller market coverage of suppliers that have tested their panels for in-plane diaphragm loads. So to think about that first way of doing things, if we start on the left, we use some of our overseas guidance, and we design a beautiful CLT diaphragm, and we try and force it through. By forcing it through, we might constrain the number of suppliers who can compete for the project, or we might have to, at the last minute, potentially insist on some additional testing to demonstrate that a proposed product can resist our diaphragm loads. And this is all sort of, that's sort of the theme of we've created some constraints. We're building costs into the project, and we're creating tension in that project where perhaps we don't need to create that tension. So alternatively, we can start over here on the right, and we've got this current market supply. We've got a number of suppliers who are operating in this middle space. They've got their compliance pathways set up for gravity spanning panels. So if we're meeting the market and using the product as intended, we just use our CLT for the gravity loads only, and we find an alternative means to resolve our diaphragm actions, and that might be a thin concrete topping. And there's a reasonable amount of international precedent for doing that, and for that being cost comparable to try to push through a pure timber building with a CLT diaphragm. There are different reasons that we might favor each approach. So as I said before, like if we're doing something really novel, then yes, perhaps we start on the left-hand side and we work really hard to make it work. We all, we do the work of getting everyone excited about the project and happy to do that extra mahi and create something special. That's not every project we should be picking and choosing. Alternatively, coming at things from the right-hand side, if we are wanting to chase scale and chase economy, then perhaps some of these sort of standard, established, or kind of boring solutions are okay, and they will help us more readily scale up and increase the number of timber buildings that we will get to design and construct. Perhaps my sort of final thoughts on this theme of meeting the market where it is. I pulled this text here off a sort of random website, and it's kind of interesting. Reading it, it could very easily be about CLT. It talks about fast installation, reduced costs due to less on-site labor, sustainability, reduced material usage, all these sorts of things. Nice finishes. But it's actually a blurb describing precast, pre-stressed hollow core floors. And hollow core floors are an example of where we, as an industry, took a product and tried to force it to do something it wasn't equipped to do. We took something that was very good at gravity spans, and we've tried to sort of put it into some very flexible, ductile structures. Hindsight is, of course, 2020, but I think it sort of shows the importance of meeting the market where it is and working within the bounds of the manufacturer's testing and processes to create, I guess it's maybe a straightforward or a longer lasting, resilient outcome. Yeah. So anyway, that was perhaps a slight sort of bleak note, but this is sort of wrapping up really. Everything we have talked through today is, of course, general guidance. It might not be applicable to every project. That is the beauty of being a consulting engineer, right? There is always a fresh puzzle to solve. So it's refreshing those three themes. Let's not try and plug gaps in our compliance pathway with hope. Let's have a little bit less of the hope and more of the harmony. Try and view our specifications as a communication tool. So getting those assumptions, out of our calc package and into the specifications and across to the fabricators, across the contractor, so they know what rules they need to be working within. And meet the market where it is. If we have products that have got the right paperwork, and if we work within that paperwork, then we can really be quite streamlined and efficient. So so one of the aims perhaps of this was to kind of perhaps provoke a little bit of discussion and create some food for thought that we can all chew on over the summer break. So see if Bjorn has popped up, so hopefully we've got some good Q&A discussions coming up.
Yeah, thanks, Matt. That was excuse me, it was a brilliant demonstration of what is possible and where there are significant gaps still to close. I love the last slide and how you elaborated on trying to bring these two sectors of the actual supply market and the compliance together, and what it means if you want the narrow Goldilocks zone, or if you're more leaning towards the market supplier for the boring but yet probably efficient design methods that are available. We have not many questions, which is probably an indicator of your presentation being quite thorough and well explained, showing where the gaps. So, but nevertheless, let's jump into it.
Whilst their lunch.
Have you thought about this in the context of timber bridges? Is the question we have currently up on the screen?
A little bit. And it probably is the same kind of ideas of we have our various materials manufacturers available to us, and thinking about using those building blocks we have to create a bridge, rather than designing a steel bridge and trying to sub in timber. I mean, there's a lot of discussions, and I think we had a conference very recently that covered that extensively. But yeah, I've given it a passing thought, but I don't see any particularly big barriers to why these three themes, say, couldn't also be applied in a bridging context.
We've got a couple more coming in as we go through the Q&A. How mature is the regulatory compliance side of things when compliance needs to be demonstrated using a selection of international standards, which might be a project-specific combination? Does this lead to problems, and how can they be resolved?
I assume we're talking about consenting authorities. I suppose my experience is probably around Wellington City Council there. They are, I think, learning very quick. So perhaps 3, 4, 5 years ago, they were sort of accepting CLT and not necessarily understanding what it was. They're sort of like, oh, it's just like Lulam, and missing a lot of the nuance just because there's novel technologies. It takes a bit of investigation to understand them. More recently, they have been doing a reasonable amount of upskilling and understanding of the different alternative solutions, and they are, I guess, appreciative of having those compliance pathways mapped out for them. So yes, it can lead to difficulties. And I guess the way we've sort of resolved it with projects is to turn up, I guess, forearmed and with that openness of, yes, there is lots of little bits and pieces of international guidance that we've used. But here is how we have pulled it all together, and sort of taking them through that process and that design basis. And that's not specific to timber. We use other novel technologies and need to work through a similar process with councils, helping them understand where it sits within that framework. Yeah.
Yeah, I guess it totally depends on the area, which ideally it shouldn't for a material, and you should have the same approach everywhere in a country. So we do need to work on that all together to educate and probably find a clearer pathway forward, which is leading into the next question here. Is there a timeline or a plan to get a cited compliance pathway in for timber construction? So do you want to share a few words about that, or are you able to share a few words? I think it's a very general question.
I mean, I'd be speculating, to be honest. There's some things happening in places around in the material standard spaces, but I don't know if there's much around fabrication and erection. It's probably the nature of these things is they do need, or they're currently set up to be reliant on push from industry and funding from industry to make those sorts of standards happen.
Yeah, I agree. And I think to move forward, we need to align with our big neighbours, Australia, to get a harmonised standard together in all of those things. I believe to have a clear way forward. And I'm aware there is things moving in the design part, and as you said, there are things moving in the material part of selected materials, yet not covering all of them again. But with regards to construction, I'm unaware of anything happening at the moment to be more specific. There might be something covered in the new design standard, which would be helpful. and desirable, but I don't know if that will find its way into it. So it's probably a good idea to pass it on and maybe implement it in the future. But apart from that, we don't know anything about it either. So if there's nothing else to say, I see the questions we had were all answered. Well, we get one more in, and we're going to do this. A lucky last before we close the webinar. Could you please share your understanding on cost of timber construction compared to other conventional structural materials? Also, what is the current drive and motivation in the market to promote timber construction? I'll leave it to you, very general, but got 4 minutes to dwell on this.
Yeah. So I suppose in terms of cost, I think the leanest timber designs are sort of able to land within 5% of the conventional materials. So there is still a small premium, but that is decreasing with every project as everyone learns more and identifies where there's costs creep in and how we can kind of iron those out. I mean, the current drive in the market predominantly, I suppose there's two drivers. One is there's a look and feel of timber construction. It's got a very different internal environment to it that has appeal to building owners, to tenants, to designers. And there's also a sustainability driver. So, the Green Star requirements continue to ratchet up in terms of the amount of upfront carbon reduction that needs to be demonstrated. So, switching from a conventional steel concrete structure to a mass timber structure, there's a significant upfront carbon reduction, and that helps greatly with achieving those Green Star ratings.
All right, time 2 minutes quickly to squeeze in this one. I think it's important to mention. How do you address subcontractors' qualifications? The person here has said, I've had issues with mass timber installers being out of their depth. Do you set out a minimum number of years of experience or do this another way? What's your thoughts on that?
It would be very difficult to set out a minimum number of years because there's probably, there's only a few years of experience accumulated in the industry so far. Typically have looked to manage it by doing sort of prototyping or sampling processes. So making some assemblies in advance so that they can kind of train and identify issues. But it's, it's sort of, again, that's kind of, working with what we've got, as we've only got the levels of experience in the country that we have. So, from a design side, perhaps we, again, take what we've got and make sure we have a design that's as tolerable as it can be, or as simple as it can be, to suit the experience of our installers, until that experience grows.
All right. There's one, it's not a question, it's more a comment, and I think we use this to conclude this. Thanks in advance, Matt, for the beautiful laid out presentation and for guiding us through what we do in specifications. Mario Benitez says, we need to convey all this information to tech colleges and universities. Companies are driven by profit, and some of these measures will reduce the profit, hence quality of work will suffer. I think that's a good word to conclude this, and thank you again, Matt, and to our sponsors, and we'll see you all in the new year with a new topic and some interesting webinars about timber and connections. So far, have a great Christmas and a Happy New Year.
Thanks.